So continuing, this is an example of an isotope. If you look, all three of these have something in common. All three technically have one proton. If you look at a periodic table, one proton automatically means hydrogen. But if you look as well, the number of neutrons varies, right? Technically, all three of these are hydrogen, but they are isotopes of hydrogen. And because scientists have to be very, very complicated about everything, this is called hydrogen, this is called deuterium, this is called tritium. But technically, they are all still hydrogen. An isotope is a variant of an element. It has the same number of protons, but different numbers of neutrons. Therefore, isotopes will all have the same atomic number. For isotope 1, 2, and 3 in the example, all of them have an atomic number of 1. Why? Because the atomic number is the number of protons, and it's one proton, one proton, one proton. It hasn't changed. Now, the atomic mass, that's listed as an average. We just saw that in that last slide of the elements naturally occurring isotopes. So, Avogadro's number. If you've ever had any type of chemistry in high school or anything else, you've probably heard of Avogadro's number and the mole. And when I was in school, anytime they talked about Avogadro's number and the mole, they always showed me a picture of an avocado and then a rodent and said, see, it makes total sense. And I was sitting there going, what? That doesn't make any sense at all. What are you talking about? So, you know how we kind of have a standard number for, let's say, a pack of donuts that we buy, or eggs that we get, or cookies, maybe. Let's say a dozen, right? A dozen is a way of saying what? A, a dozen means 12, right? So that's kind of just this standard number we have. You go, you get a dozen eggs, you go, you get a dozen donuts, you go, you get, I don't know, a dozen empanadas, you go and get a dozen whatever. And when you say a dozen, it means 12, right? That's all this is. So they wanted kind of a standard number of atoms. So what they did was they said, okay, we're going to take carbon 6 and we're going to measure out 6 grams, and whatever that number is, it'll be our standard number. And that was 6.022 times 10 to the 23rd atoms. Okay, that's how many atoms are in 6 grams of carbon 6. So this became our standard number. The thing is, if I wanted to measure that out, I didn't want to say, I want you to measure out 3 times 6.022 times 10 to the 23rd of phosphorus. That's a pain, so we don't do that. We had to kind of come up with a shorthand name. So the name that we came up with was the mole. Just like dozen means 12, mole means 6.022 times 10 to the 23rd atoms. Now, Avogadro, that person, was the one that came up with the idea of coming up with that whole, this is our standard number. So they also call it Avogadro's number. So Avogadro's number and mole mean the exact same thing. It's just the difference of saying 6.022 times 10 to the 23rd versus saying a mole, like saying 12 versus a dozen. It's just a kind of shortened way, a nickname way of saying the same thing. So there are rules for atoms, okay? The atomic number in a perfect world will equal the number of protons, electrons, and neutrons in that atom. Again, in a perfect world. The problem is that there are also rules that have to be followed when it comes to things called valence shells that the electrons occupy. So we're going to use one of the perfect examples. Okay, we're going to use argon to go through these rules. And for the sake of argument, I want you to think of a peanut M&M. Okay? So in a peanut M&M, You've got the outside that has the candy, right? Inside of that, you've got, where it is orange, you've got the chocolate layer, right? Chocolate. And in peanut M&Ms, you know as well as I do that every now and again, you can see the skin of the peanut outside the peanut, right? So let's say this is the skin of the peanut. Okay? With me so far? Each one of these layers, the skin of the peanut, the chocolate, the candy, is what we call valence shells. They are layers of electrons, okay? So, the first rule applies to the first shell. The first shell holds 2 electrons to be stable. Okay? So argon. Argon has 18 protons. In a perfect world, that would mean 18 protons, 18 neutrons, and 18 electrons, right? Again, perfect world. Ah, unicorns, rainbows, dragons. So let's draw that. 18 protons. Now remember, protons and neutrons exist inside of the nucleus. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 protons. Neutrons are also in the nucleus. So let's draw that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Now, what was our first rule? Our first rule was in the first shell, the skin of the peanut, we have 2 electrons to be stable. So here's my first shell, 1 electron, 2 electrons. Does that equal 18? No. So we still have technically 16 more electrons that are unaccounted for, right? So let's talk about the second rule, which is actually second and third. So the second rule is called the octet rule. Okay? Octet, what do you think of? 8. So the second and third shell must have 8 electrons to be stable. Okay? So we're moving from the innermost shell that can at most hold 2 to the second shell. Now, the second shell is going to be the chocolate up here in my M&M. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Now, if we count everything, we've got 8 in this outer one, 9, 10. We only have 10 electrons. Does that equal to our 18 up here? No. So we have to go out to our third shell. So our third shell, which is going to be the candy portion of our M&M, we've got 10, 11, 12, 13, 14, 15, 16, 17, 18. Now remember what I said. The octet rule says in order for an atom to be stable, there has to be 8 in the second shell and in the third shell. This atom is very, very stable. And it's very, very stable because everybody's full. My first shell has 2, as the rule states. My second shell has 8, as the octet rule says. And my third has 8, as the octet rule says. Now, something to keep in mind for us in A&P, we don't get any more complicated than this. This is as complex as we get. Okay? So, these are the rules that you need to be aware of. And if your atom is not following these rules, there has to be a change made. Because if you have 7 instead of 8 in the third shell, you have a very unstable atom. If you have 1 instead of 2 in that first shell, you have a very unstable atom. Nobody wants an unstable atom because that's where things explode. Okay? So now we know our rules. When you look at the periodic table, we're always going to start as if we have perfection. We're always going to look at the atomic number and say, okay, so we've got this many protons, which means we have that same number of neutrons, which means we have the same number of electrons. And then we'll fiddle with it by following the rules. So, electrons and chemical bonding. The ability of your molecules in your body to come together and make things like cells, to make things like protein, to make things like carbohydrates, is all dependent on those atoms' ability to bond to each other. Okay? And it involves the outermost ring of electrons in its valence shells. They can be transferred or they can be shared between atoms. These types of things are called chemical bonds, okay? And we're going to talk about 2 major types of chemical bonds. We're going to talk about ionic bonds and we're going to talk about covalent bonds. So let's start, hang on one second. Let's start by talking about ionic bonds, okay? So, an ion is an atom with unequal numbers of protons and electrons. Okay? So that basic definition is what an ion is. It's got different numbers of protons versus electrons. So I'm going to go back here and I'm going to say, let's look at sodium. Sodium is right here at number 11. Okay? So, in a perfect world, sodium is at number 11, right? So what does that mean? It means I've got 11 protons, I've got 11 neutrons, again, perfect world, and I've got 11 electrons. So let's draw that. 1, 2, really? Ugh. Sometimes I like this tablet, sometimes it drives me crazy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons. Neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In the nucleus, right? So, first shell. How many does the first shell hold, guys? What's the rule? 2. So I've got 1, 2. Second shell. How many does that hold? Octet rule, right? So that's going to be 8. So I've got 1, I've got 2, 3, 4, 5, 6, 7, 8, 9, 10, because 8 plus 2 equals 10. Am I at 11 yet? No. So let's go to the third shell. Which direction did I just go? Hang on. Let me redo that. Third shell. 11. Am I happy? No. How do I know I'm not happy? Because I'm not following the octet rule. According to the octet rule, that third shell should have 8 electrons. Do I have 8 electrons? No, I've got 1. What can I do? Well, I'm sure there are some students saying you could share. The problem with sharing is I can only share what I have. So I've got 1. If I share, I only get 1 back. That would only leave me with 2 electrons in that outer shell. So that doesn't work. I can't do that. So what's the easiest thing to do? Get rid of it. I don't need it. So if I just let it go away, right, then I let it go away. Now, this is kind of the interesting part about this, though. How many electrons do I have right now? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Count them. There's 10 of those, yes? So I have 10 electrons. Let's count how many protons I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 protons, right? So that's 11 protons. What's the charge on my protons? Positive. What's my charge on my electrons? Negative. Yeah? Okay, now this is where things get kind of interesting. If you cancel them out, I've got a negative and I've got a positive, that equals 0. I've got +1, -1, that equals 0. Well, take that one out and this one out. This one out and this one out. This one out and this one out. This one out, that one out. This one out, this one out. And I'm just canceling them out. That's all I'm doing because I've got a positive and I've got a negative, right? Notice that I am completely out of electrons, but I still have 1 extra proton. I've got 11 protons and 10 electrons, so I've got an extra positive, yes? This is an ion, an atom with unequal numbers of protons and electrons, right? Well, now I have unequal numbers. I've got 10 electrons and 11 protons. So this is an ion. If I want to be more specific, this is a cation. Okay? Cations are positive. So cation is a positive ion because it has more protons than electrons. Whoops. Now, it may be something like sodium. And in this case, a lot of times, if you've ever seen sodium written in a chemical formula, they'll say Na plus. That plus is because of that extra proton. That's why they say that. Okay? So, let's talk about chlorine. Ta-da. Chlorine is up here. What's my atomic number? My atomic number is 17, right? So, sodium was at 11. Chlorine. This is a lot easier on an actual whiteboard, guys. Sorry. Okay, chlorine is at 17. So in a perfect world, we would have 17 protons. Seventeen neutrons. I'm not sure why it's doing that, guys. And 17 electrons. So again, let's draw that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 protons. Neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And finally, our electrons. First shell, 1, 2. Second shell, 3, 4, 5, 6, 7, 8, 9, 10. Again, don't know why it's doing that. Third shell. We've got 10 so far. Do we have 17? No. So there would be 11, 12, 13, 14, 15, 16, 17. What do you notice? Do I have 8 electrons in the third shell? Does it follow the octet rule? No. So this is an unstable atom. This is an atom that can cause an explosion. This is bad. So what do? Well, if you say share in this case, then yes, because what do I need to make 8? Just 1. So if I share 1 and I get 1, technically I have 1, 2, 3, 4, 5, 6, 7, 8 in that outer shell. I do have that. 1, 2, 3, 4, 5, 6, 7, 8. But we kind of are in a unique situation in the fact that sodium has completely given up an electron and it's just floating around. So why don't we just take it? So we take that extra electron. How many do I have in my outer shell now? 1, 2, 3, 4, 5, 6, 7, 8. So as far as my atom's concerned, it's happy. The rules are followed. I have 8 electrons in the third shell. Now, this is the only thing. How many protons do I have in that chlorine? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I have 17 protons, right? So I have 17 protons. How many electrons do I have? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 18 electrons. So 17 protons, 18 electrons. It's unequal, right? So if you have ever seen chloride written, they'll usually put Cl minus. That minus is because of that extra electron. An unequal share or an unequal number of protons versus electrons. Now, positive was a cation. When you've got a negative ion, that's called an anion. Okay? So, we've got one atom. Actually, I'm going to switch. We've got Na plus and we have Cl minus. What's that phrase in that Paula Abdul song? Opposites attract, right? So Na plus is attracted to Cl minus literally because of the different charges. Okay? That type of bond between a positive and a negative electron. Oh, really? That charge difference and that bonding that's caused, by the opposite charge difference is called ionic bonding because you have ions bonding to each other. Normally, atoms are electrically neutral. If you've got the same number of protons and the same number of electrons, you don't have any charge to it. But when you don't, when you gain or lose electrons, then you get ions. Okay? You get ions. Now, positively charged, it's called a cation. Why is it positive? I have more protons than electrons. Negatively charged or an anion, I have more electrons than protons. So in ionic bonding, it's when the ions of opposite charges attract each other and remain close together. So sodium chloride, that's table salt. You'll notice that your table salt comes in crystals. It looks like little cubes. One of the reasons is because it has to be arranged in that positive, negative, positive, negative, positive, negative in order for it to actually bond. If you try and put a negative and a negative together or a positive and a positive together, they don't like each other. Okay, so that is ionic bonding.